This video is a continuation of Chapter 13, Fundamental Equilibrium Concepts. This is the video presentation for Section 13.3, which covers the concept of Le Chatelier's principle. Before watching this video, make sure that you have completed the reading guides for Section 13.3 from the textbook. Have your copy of the Chapter 13 handouts handy so that you can take notes as we work through this section. Le Chatelier's principle says, if a change in conditions is imposed on a system in equilibrium, the equilibrium position will shift in a direction that tends to reduce that change. In other words, if a system is at equilibrium and you alter the system to make Q not equal to K, the system will react in such a way as to make Q again return to a value of K. Let's look at the reaction of N2O4 gas molecules dissociating into two molecules of NO2 gas. This reaction is endothermic with a delta H value of 57.2 kilojoules per mole. We can write expressions for the reaction quotient Q and the equilibrium constant K by showing the concentrations of products raised to the power of their coefficient in the balanced chemical equation divided by the concentration of the reactant. If these concentrations are not equilibrium values, our ratio gives us the reaction quotient Q. If, on the other hand, these are equilibrium values, this ratio gives us the equilibrium constant K. We're going to start with a system at equilibrium with constant values of the products and reactant, a system that is at equilibrium. What happens if we add some product, NO2, to this system? Adding NO2 puts a stress on the system, indicated by the green line. Notice that the concentration of NO2 immediately increases upon its addition. What does this do to the value of Q? Since we've increased the concentration of the product, our numerator in our reaction quotient is now bigger than it was before. This means that Q is now greater than K. How should the reaction shift to reestablish equilibrium? Since Q is greater than K, we need the reaction to shift in the reverse direction to use up some of the product that we've added and generate more of the reactant. The reaction will proceed towards the reactants until Q is equal to K. Notice that the new concentration values at equilibrium will be different than the original equilibrium concentrations. Why does the reaction shift in this direction? Adding NO2 initially increases the rate of the back reaction, so the concentration of NO2 will decrease and the concentration of N2O4 will increase, at least from their new positions. The concentration of reactants and products at the new equilibrium are different than the original equilibrium, but the value of K stays the same. Let's look at another example where instead of adding product, we're going to add some of the reactant N2O4. Again, we start with a system that is at equilibrium and introduce a stress to the system. Adding N2O4 causes the concentration of N2O4 to immediately increase. What effect will this have on the reaction? It will cause a shift, but in which direction? Since we've added N2O4, if we evaluate our Q expression, we have now made the denominator a larger number. This means that the value of Q is going to be less than K. This will cause the forward rate to increase. This will increase the concentration of product and decrease the concentration of the reactant over time, until a new equilibrium position is established. Again, notice that we reach an equilibrium where we have constant concentrations of reactants and products, but these values are different from our original system. This is because we've added molecules to the system. What hasn't changed is the value of K. Sticking with the same example of the dissociation of N2O4 gas to two NO2 molecules and starting with the system at equilibrium, what happens if we double the volume of the container? If we double the size of the container, we will actually cut both concentrations of reactants and products by a factor of 2. This is shown in the graph above. What effect will this have on the position of equilibrium? Are we still at equilibrium? To evaluate this, we need to evaluate the value of the reaction quotient Q. This is shown in the following equation. Notice that what we've done is taken our equilibrium concentrations and multiplied both of them by 1/2 to represent the doubling of the size of the container. However, in the numerator, we also have a power of 2. If we rewrite this, in the numerator we have 1/2 squared times the equilibrium concentration of NO2 squared divided by 1/2 the equilibrium concentration of N2O4. We see that one set of halves will drop out, giving us a value that is now 1/2 of our original Kc value. This means that Q is less than K. Whenever Q is less than K, it will cause the reaction to shift in the forward direction to increase the value of the reaction quotient until it's equal to K. If we look at the graph above, this causes the reaction to shift. The concentrations of products will increase from their new position, and the concentration of reactants will decrease. We'll reach a new equilibrium position with constant values of reactants and products, but note again that these new values are not the same as our original. However, the value of K has not changed. Whenever we change the volume of the container, the direction of shift is going to depend on which side has more molecules of gas, or in the case of an aqueous reaction, which side has more dissolved species in solution. In order to determine which way the reaction will shift, you need to evaluate the value of Q and see how it compares to the value of K. What are some other changes that we could do or stresses that we could make on a system at equilibrium? For example, what would happen if we added an inert gas, say something like nitrogen, that doesn't react with either the reactants or products? What effect does this have on the reaction quotient Q? Since nitrogen doesn't appear in the reaction quotient Q, this causes no change to the system. As we've already mentioned, if we add water to an aqueous solution, this has a similar effect as doubling the volume of a container for a gas system. You would have to evaluate the value of Q to see which way the direction will shift. Temperature changes for reactions are a little more complicated, and the resulting shift depends on whether the reaction is endothermic or exothermic. In this case, we had an endothermic reaction with a positive value of delta H. Remember that endothermic reactions can be written with heat as a reactant. Le Chatelier's principle says that whatever stress we put on a system at equilibrium, the reaction will shift in a direction that tries to undo the change that we've made. So raising the temperature on an endothermic system will cause the reaction to shift towards products to use up the added heat. Notice since we've made no other changes, this means that the value of K must increase. As we mentioned in one of the first videos, the value of K is temperature dependent. Let's summarize what we've learned about Le Chatelier's principle. One of the most important things to remember is that the value of the equilibrium constant K does not change when you change concentrations of reactants or products. It only changes if you change the temperature. However, equilibrium concentrations of reactants and products can change and have different values even for the same reaction and the same value of K. If we add reactants or remove products, we will cause the reaction to shift in the forward direction to try to undo the change that we've made. Conversely, if we add products or remove reactants, the reaction will shift back towards reactants. Changing the volume or pressure of a reaction, the shift will depend on the reaction. You have to evaluate the value of Q. When you decrease the volume of a reaction, the reaction will shift to the side with fewer gas molecules. On the other hand, if you increase the volume of a reaction, the reaction will shift to the side with more gas molecules. What about changing the temperature? Raising the temperature will cause the reaction to shift in the forward direction for endothermic reactions, and we'll see in later sections of this chapter that this causes the value of K to increase when you increase the temperature. However, exothermic reactions, raising the temperature, causes the reaction to shift backwards towards reactants. This means that the value of K actually decreases with temperature for exothermic reactions. In this video, we've explored the concept of Le Chatelier's principle. You are now ready to attempt the Chapter 13 group problem number 10.